Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting first lecture for week number 3 for our course of communication systems. If you recall, in our last lecture we talked about signals and spectrum, and we discussed that signals can be represented in time domain as well as in frequency domain, and we discussed how we can represent a signal in a frequency domain. The mathematical tool that we use to transform any signal from time domain to frequency domain or from frequency domain to time domain is Fourier transform. Really, for periodic signal we need to use Fourier series, whereas for non-periodic signals we need to use Fourier transform. And I mentioned that we will be relying on the standard tables for Fourier transform in order to simplify our calculation. Wherever we need to use any Fourier transform, we will generally refer to the table which are also available in appendix of your textbook. So in today's lecture we'll start our discussion with the same topic but from the perspective of systems. From the beginning of our lecture I am mentioning that we have to deal with two different aspects. One is the signal that we actually discussed in our last week's session, and second is the physical hardware or physical system through which that signal passes. So in today's discussion we'll talk about signal transmission, and typically through a linear system. Typically the system that we use is linear system, although there are non-linear systems as well in the real world scenarios, but most of the analysis related to communication systems is related to the linear time invariant systems or LTI systems. So for this course, of course, we will be discussing only LTI systems, so that's why I have restricted the discussion on the linear systems. So whenever a signal transmits from a linear system, so we can treat that system as a black box actually, and you would see that whenever we apply an input to that particular black box, it will produce an output. So in other words, a communication system is actually transforms, or any system, not only communication system, any system transforms an input quantity or input signal into an output signal. So we can ideally we can represent that system by using a block so that we can relate the input and the output. From point of view of communication systems, of course, this system is actually a two-port network. You can see that generally we have one input port and one output port. So our system is actually providing a transformation from input to the output. So we can have a two-port network. We can represent the system as a two-port network, which is actually driven by a voltage or current signal, which of course that signal would be applied to the input port, and eventually the system would make certain changes or certain transformations to that input and provide another voltage or current at the output. So this diagram is actually an illustration of generalized linear system. So we have one input and one output. So system is basically transforming that input into the output quantity. The question that we are dealing with here is that how we can represent this linear system mathematically. Of course, in our calculation or in our analysis, we need to represent the system in a mathematical way so that we can include the properties of the system in our analysis. Looking back at the system, of course, how we define the system, you should pay focus on that. the system is basically defined as something which is relating this input to the output uh, signals. So basically system should be defined in terms of these transformations. So how do system transforms this input quantity into the output quantity? So a reasonable system description should tell us how we can which type of output we will get to a particular input. So any mathematical representation should relate these two quantities, that is input and output. So mathematical description of the system is actually you can say that it can actually be in form of a input output equation. So this is one of the basic representation of the of any linear system. We try to make a equation that through which we can relate input voltage or input current to the output voltage or output current. So basically is relating the input and output quantity, so that if you know the input, you are able to calculate the output. So just an analogy you have in your previous course of circuit analysis, you must have done some calculation where you are given a circuit and you try to calculate the output voltage when you are given the input voltage. So whatever we do, like if you recall, if you do the mesh analysis or nodal analysis, and eventually what you get is a form of a differential equation, and by solving that differential equation you can easily calculate the output voltage whenever the input voltage is given. So this is one of the basic representation of any type of system, and I must mention that this representation is not only true for linear system, rather it is also true for non-linear systems as well. So we can use this input output equation technique to represent the non-linear systems as well. However, for this course we will be only focusing on linear systems only. In real calculation and real systems, typically whenever we try to calculate or try to form the equation of a system, typically we get a differential equation. So the analog systems, generally they are represented by a specific type of differential equation, and by solving that differential equation you can easily calculate the output voltage or current if you are given the input voltage. As I mentioned, the most basic representation is this one, although for the analysis of communication system we generally rely on another important representation, which is named as impulse response. Impulse response, remember that I am talking about a linear system, so whatever we will be discussing here would be related to linear systems. So we are for the time being ignoring any type of non-linearity that may be present in that system. So impulse, what is impulse response? First of all, I must want to focus on this term, this response term. Whenever in the analysis of system, whenever we refer to this term response, that means we are referring to output side. So whenever we say impulse response means we are referring to output of the system when you have applied an impulse function at the input. Impulse function we have discussed in our previous lecture. So if we apply an impulse function at the input side, eventually you would get certain output. So that output which you get when you applied an impulse at the input side is named as impulse response. Another term which is commonly used, although we are not representing it here, which is another term which we use is step response. So you should be able to realize that what is a step response. Step response means the output that you get when you apply a step function at the input side. So mathematically, how we define this impulse response? This impulse response is the output of the system when you have an input applied a unit impulse function at the input side. As I mentioned, any suitable description of the system should provide enough information in order to calculate the output whenever an input is known. Similarly, this impulse response also has this property. If you know the impulse response of any system, T if it is given, Ht is actually representing the impulse response, and if you know the input, let's say I am representing the input by xt, in that case you will be able to calculate the output, and that output is calculated by convolution. So if you convolve xt, the input, and ht, the impulse response, you would get output of the system. And remember that the convolution is a commutative operation, so it doesn't matter whether you convolve xt with ht or ht with xt. So changing their order would not change the output quantity. So you can see that impulse response has the sufficient information to calculate the output of the system whenever the input is given, and you need to perform this convolution operation. So basically this ht or impulse response is actually the time domain representation. You can focus from here. I have mentioned this h as a function of time. So mathematically this ht is actually a time domain representation of the system. So basically by representing the impulse response, we are representing the behavior of the system in time domain. As I discussed, in the case of signals, we can represent the signals in time domain as well as in frequency domain. Similarly, any system can also be represented in time domain or in frequency domain. In frequency domain, representation means how a signal would be affected by the system whenever the signal is represented in the frequency domain. So actually it would be representing the frequency dependent properties of the system. So we generally call that frequency domain representation as frequency response, and or sometimes some authors they prefer to write it as transfer function. Transfer function or frequency response, they are actually the representation of the system in frequency domain. Again, you should realize that impulse response and frequency response, they may be representing the same system, but they are representing the system in different domains, that is time domain and frequency domain. So these two, impulse response and the frequency response, they are actually Fourier transform pairs of each other. So if you get the Fourier transform of impulse response, you would get this transfer function, or if you calculate the inverse Fourier transform of this transfer function, you would get the impulse response. As I mentioned earlier that we typically we use frequency variable f, but some authors they prefer to write in terms of omega or radian frequency omega. So frequency response can be represented in terms of f or omega. It does not make any difference, as we know that f and omega, they are related with a constant multiple which is 2 pi. So if you multiply f with 2 pi, you would get omega. So we can represent both of them simultaneously. One of the important thing related to the frequency response is that it is a complex number. When we were talking about the spectrum, if you recall in the frequency domain, when we are talking about the signal, we talked about the spectrum, and we discussed that whenever we transform a signal into frequency domain, in that case we typically get a complex number, and complex representation, eventually you get a two-sided spectrum. Similarly, when we represent a system in frequency domain, or in other words, frequency domain is representation is this transfer function or frequency response. So whenever we calculate frequency response of any system, so that will be a complex number, and we know that each complex number has two important characteristics, which is amplitude and phase. So eventually the system behavior should be represented by two important sides, which are amplitude and their phase, and they are separately known as amplitude response and the phase response. Amplitude response means what changes system would make in the amplitude of the signal, and phase response represents what type of changes the system will make in the phase of the system. So these are integral part. Amplitude response and phase response are the integral part of the frequency response. So whenever you calculate frequency response, that means you would be getting both type of responses, that is amplitude response as well as the phase response. So this is a graphical illustration of the system. So we have a LTI system. At input side, if you apply a function xt, that means you will be getting an output yt. And as I mentioned, this impulse response is actually represented as this impulse response will get when the input applied is delta t, impulse function. So if we apply delta t, the output that you would get is actually ht. And in frequency domain, if you transform this delta t into a frequency domain, that comes out to be 1. And if you transform this ht in frequency domain, it comes out to be the frequency response of the system. So these quantities, they are related to each other. If you transform, if you change the domain of ht, you would get the frequency response of the system. If you know input, you should be able to calculate output if any of these impulse response or frequency response is known. If you are working in time domain, in that case you should convolve the applied input function xt and convolve with this impulse response, and the result of this convolution would give you the output of the system that you would get after the signal passes through this LTI system. Similarly, if you are working in frequency domain, these arrows, they are showing that it's frequency domain transformation. So we are using Fourier transform to represent the system in frequency domain. So if we are solving the signal in frequency domain, and we have applied this x of omega signal onto the system, so of course you would be getting another output, which is actually the frequency domain output, which I have represented as y of omega. This output is actually calculated by simple multiplication of x and h, where h is this frequency response and x is actually the transform of the input signal. If you recall from your study of Fourier transform, the convolution, whenever this convolution is calculated in frequency domain, so that convolution becomes simple multiplication. So you can see from this expression here as well, the output in frequency domain is actually calculated by simple multiplication, not the convolution. But in time domain, you need to perform the convolution. So this is the overall discussion related to how we can represent a system in time domain as well as in the frequency domain. As I previously mentioned, that for communication systems, the frequency domain representation is very much important, because in many cases we analyze our system at specific frequencies. So we generally prefer to analyze the systems and signals in the frequency domain. So in many cases we will be dealing with the frequency domain. So let me briefly talk about this frequency domain representation as well. I have mentioned that this HF, the frequency response, is actually a complex number. So being a complex number depicts that it should have certain amplitude and it should have certain phase, which is represented as argument of HF. So this arg of HF is actually representing the phase, and you can see that this is actually dependent on frequency. Similarly, this modulus here is actually representing the amplitude. So each frequency response is comprises of two parts. One is the amplitude response, and other is the phase response. And output of the system, as I said, output is actually calculated by multiplying the transfer function with the transform of the signals, input signal or spectrum of the input signal. So output is actually mathematically represented as HF multiplied by XF. But we know that for output, again, there are two important properties. One is its amplitude and second is its phase. So we can individually calculate amplitude and phase of the output as well. How we can calculate amplitude and phase? If you need to calculate amplitude, so amplitude of the output function is actually equal to product of the amplitude of the input and this amplitude response HF. So if you multiply the amplitude spectrum of the input signal with the amplitude response of the system, you would get the amplitude spectrum of the output. Phase is actually calculated by addition. Note that the output is calculated by the operation of multiplication, whereas phase is calculated as with the operation of addition. And it is quite logical because phase is in this power, e raised to power j omega. This part is actually representing phase. So if you multiply these two, so with same basis, the phases would get added together. So phase is actually calculated by the operation of addition. So if you want to find the phase angle of the output, you should add the phase angle of the input signal with the phase response of the system. So if you add them together, you would get the phase of the output signal. So you can see that if you know the frequency response of the system, or in other words, if you know the transfer function, you can easily calculate the spectrum of the output. And if you want to transform, if you want to calculate the output in time domain, you can easily transform it by using Fourier transform, rather inverse Fourier transform, to get the output in the time domain. Or in other alternatively, you can use this convolution operation to calculate the output in time domain. So this is how we represent a system in time domain as well as in frequency domain. And I have also described like these two equations. They are used to calculate the amplitude and phase of the output if you know the amplitude and phase of the input. I have included this slide. This one, what I'm showing here, is actually the relationship between the signal and the system. So this XF is actually representing the amplitude response of the signal. HF is representing the amplitude response of the system itself. And system can be anything. It can be channel, it can be transmitter, or it can be combination of multiple components. What type of output would you get? So I am trying to illustrate that how this system affect the overall response of the output, and for that illustration I have only shown the amplitude spectrum. You can see that there is no phase spectrum, rather I'm only focusing on the amplitude spectrum. As if you recall in previous lecture as well, I mentioned that in most cases we only show the amplitude spectrum, that because from communication system point of view they convey more information to us as in comparison to the phase. But we understand that the complete representation should include amplitude as well as the phase of the system. So in this case I want to illustrate how the output is changed when an input is input passes through different types of systems. So for this case I have shown three different cases. You can see that this input has certain bandwidth which is represented by W. So the input signal has the bandwidth W, and we try to pass this input through a system which has a specific bandwidth which is represented by B. And I have shown three different categories here. If you draw a line here, so you would see these are three different categories. In first case, the bandwidth of the system is actually much greater than the bandwidth of the signal. The first case. In second case, the bandwidth of the system is approximately equal to the bandwidth of the signal. And in third case, the bandwidth of the system is much smaller as compared to the bandwidth of the signal. So if you multiply, and if you recall, the output is actually equal to the multiplication of this amplitude of the input signal and this amplitude response of the system. And if you see, if I multiply this for the first case where the bandwidth of the system is much bigger than the bandwidth of the system, and if you multiply, you can see that this first part of the system is almost constant, and therefore if you multiply, eventually the output that you would get would be very much close to the input. And actually from communication system point of view, this is our required condition, because the objective of communication system is to reproduce the information that is being generated at the input side, and we want to reproduce the same information at the output side. So this is the actual requirement that we generally want to have in a communication system. So you can see that if you want to have ideally the same output, we must have a bandwidth of the system which is much bigger than the bandwidth of the signal. In second case, if the bandwidth of the system becomes close to the bandwidth of the signal, in that case you would see that the output spectrum is rather changed. So there is from time domain perspective, we would call it distortion. This one is spectrum. The term distortion generally used for the time domain representation, but you can see that this change would cause some sort of information loss. However, you should realize that the overall spectrum of the output is actually very much close to the output of the input signal, although there are changes, but still the signal can be easily recognized at the output side. So even in this case, we can have a useful information for the system, and eventually the output signal that you would be getting would be able to convey the information that you intend to transmit. For the third case, I have taken a special case where the bandwidth of the system is actually much smaller than the bandwidth of the signal. So you can see that the bandwidth of the system is very much smaller, and if you multiply these two, you would see that because this amplitude is way smaller than the amplitude spectrum of the signal, and if it's multiplied, so all this part would be actually gone, or would have very low amplitude in the output side. And you can see that the spectrum of the output signal is significantly different than the spectrum of the input signal. Or if you look in the time domain, you would see that the shape of the waveform that you would be getting at the output side would be significantly distorted, and you would not be able to originally recover the information that you intend to transmit from the input side. So you can see that the bandwidth of the system is also much important, because if we try to pass a relatively wide band signal with a narrow band system, eventually we will not be able to make a useful transmission. So ideally we intend to have this case, so that the signal bandwidth, system bandwidth is much greater than the bandwidth of the signal. But of course, as we have previously discussed as well, the bandwidth is one of the important resource that we want to optimize. So we generally do not use this condition, rather we focus on this case where the bandwidth of the system is almost or close to the bandwidth of the signal, because in that case, although there is some changes, but still we are able to have a useful communication, and we are able to transmit the information that is available at the input side to the output side. So our purpose is fulfilled in that case, and with utilizing a relatively smaller amount of bandwidth of the system. So these curves, they are actually arbitrary curves, but I have tried to illustrate how the signal transmission gets affected by the bandwidth of the system. So it is therefore significantly important to realize how the system would behave in the frequency domain. So only time domain representation would not be sufficient in many cases, because from our point of view, the frequency dependent nature of the signal as well as the frequency dependent nature of the system is actually they play an important role for the analysis. So therefore we sometimes refer to the several times refer to the frequency domain analysis of the system through the Fourier transform. So concluding the today's discussion, we talked about systems in continuation to the discussion that we had last week regarding signals. And as we have previously discussed that signals can be represented in time domain and frequency domain, similarly a system can also be represented in time domain as well as in frequency domain. And I have shown, so this is the diagram. So these are the different representation of the system. In time domain we try to represent the system by the impulse response, whereas in frequency domain we intend to represent the system by its frequency response or transfer function. And in both cases we are able to calculate the output by certain mathematical operation. In time domain we need to perform the operation of convolution in order to get the output, and in case of the frequency domain we need to perform the operation of multiplication in order to get the output of the system in frequency domain. So we stop our discussion here, and inshallah we'll have another topic in our next lecture. Thank you all.